Welcome to our 12th learning workshop on carbohydrates. And there's lots and lots and lots of carbohydrates that we're going to try and go over today, but we'll try to keep it simple. First of all, I want to start with the basics, which is classifying carbohydrates. So classifying carbohydrates. If there is, so here's a Fischer projection of the carbohydrates, okay? Now, you will be expected to know whether or not something is a D carbohydrate or an L carbohydrate. And this has to do with dextrorotary or level rotary, but basically there's a really easy way to tell. What you have to look for is the last chiral carbon, okay? So if I'm trying to distinguish between D or L, I start numbering the chain, because remember these are carbons here. Carbon, 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 and carbon, right? And I'm actually going to shrink the size of my little pointer here. But so I can number this. I'm going to start numbering from the side closest to the double bond O. The double bond O, otherwise known as the carbonyl. So this will be carbon number 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, 6. Okay, so the last chiral carbon, the chiral carbon furthest away from the C double bond O, or the last chiral carbon is going to be carbon number 5. Okay, so the last chiral carbon is going to be carbon number 5. And you might be like, well, what's a chiral carbon? We'll get to that in just a little bit. But in these Fischer projections, which is what these are, Fischer projections, it's typically the last carbon that is shown as part of with a cross. All right, and as you can see, the hydroxide on this last chiral carbon is on the right-hand side. If the hydroxide is on the left hand, if the hydroxyl group, the alcohol group is on the left-hand side, that would be an L sugar. But since it's on the right-hand side, it's a D sugar. If we look at the next one, we could do the same thing. It's 1, 2, 3, 4, 5. 5 carbon sugar, and the last chiral carbon, the last cross, so to speak, is carbon number 4, and I see that the OH is on the left-hand side here. Because the OH is on the left-hand side, we would call this an L sugar. This would be an L sugar. Whoa. Frank, you're moving my stuff.
Shoot.
There we go.
Okay, so
yeah, just switch off that select arrow, that little arrow on the left-hand side of the toolbar. Click off of that so that it's a hand, and then you can drag yourself around with the hand. So yeah, you don't want it as an arrow; you want it as a hand.
okay.
Otherwise you'll start moving stuff on the old image. Okay. So now, as a classification for this, basically we classify carbohydrates based on how many carbons it has, and as it shows here, it's based on the number of carbons and whether it has an aldehyde or ketone group. If it has an aldehyde group, an aldehyde has a C double bond O at the end of the chain. If it has an aldehyde group, we call it an aldose, or an aldo, well, how many ever carbons it has. Since it has 6 carbons, we use the prefix hex, because hex means 6. So pent would be 5, tetra would be 4, And typically we don't see, well, okay, there are trioses, but typically we don't see trioses, or you're not going to really see trioses too much. Okay, so here's the deal. For problem number 1, this one right here, you see that this carbohydrate has how many carbons?
5.
5. And does it have a ketone group or an aldehyde group?
Ketone.
The ketone group. So what would you call that then?
Pentose. Pentane.
It is a pentose. Pentose because it is a carbohydrate. And then you get the prefix that indicates what type of group, if it's an aldehyde or ketone. So this would be a ketopentose.
Wow.
Does that make sense?
Mm-hmm.
Yep.
Okay. So now I want you. Let's go ahead and do number 2. Is this an L sugar or a D sugar?
Is an L.
Yep, because the hydroxyl on the last chiral carbon is on the left-hand side, so that's an L sugar. And how many carbons does it have?
4. No, 5. 1, 2, 3, 5.
5. And does it
5.
have an aldehyde group or a ketone group?
Aldehyde.
Aldehyde. So this would be a
Aldopentose.
aldopentose.
Oh, I see. Photographs. Hold on, let me take photograph of it.
All right.
Could
So
you take it down? Could you take it down and let me take photographs of it, please?
I'll bring it back up here.
Yeah, thank you.
No problem.
Okay, down. I'm done. Next.
Okay, so now what I'd like you to go ahead and do is, if you could, Frank, I'm going to give you problem number 3. Just do those first 2 parts, whether it's L or D, and then give the generic name. And Leanne, you want to go ahead and try problem number 4? And Linda, I'm going to have you do problem number 5.
Problem number 5. I hope I'm able to do that.
All you have to do is say if it's a D or an L sugar. And if for Leanne and Frank, you can go ahead and just write directly on it. Frank, you're 3. Leanne, you're 4. And you can also use the type feature as well. Just type it rather than...
Okay, cool.
And don't forget, you can also adjust the size at the top of the
I'm not able
squiggly lines.
I'm not able
Options.
to write on this one now. I'll just tell you. I'm not able to write on it. So mine would be
3, 4. Same.
So, no problem.
Mine would be,
Okay. Very good. It is a D sugar.
aldohexose. 1, 2, 3, 4, 5, 6.
Yeah, very good. It is an aldohexose.
Aldohexose.
That's right. Oh, and if you don't want your ink to be quite as fat, you can thin it out. And if you click on that squiggly line, the size of the thickness is up at the top. It shows the 5 different circles. The really fat circles or really thin circles. You can make it thinner if you want.
Oh, no, that's only sound. H, O, H, H, O, H. This one is L. O, H, L.
And I totally understand why you'd say butose, but for the sugars, it actually is tetrose. sorry.
It's okay.
It ends up using the other kind of prefixes rather than like, you would think your typical organic chemistry prefixes would be like methane, ethane, propane, butane. Well, in this case, for these, you actually are using the prefixes.
Is this L, is it aldo, or is it supposed to be keto? This one not keto, D4, number 4. Is that not keto?
No, number
See
4
there,
is
is
an
it L?
aldose.
It's an aldo? Okay.
Yeah, number 4 is an aldose because it has to do with where the double bond is. If the double bond is on an end carbon, then that's an aldehyde, and therefore it's an aldose. I helped you out a little bit there, Leon.
Thank you.
No problem.
Aldopentase.
5 is supposed to be aldopentose.
Mm-hmm. Yep, 3 is an
Pentose, right?
aldopentose. Very good. Yeah, 3 is an aldopentose. Very good. Cool. So now we have to deal with the Hayworth projections. And the Hayworth projections are significantly more difficult. Okay. So if I am looking at, I'll go ahead and give us an example, and I'm just going to move. Well, actually, I'm going to move this sheet below down a little bit. All right, I'm going to give 5 as an example, show you how to do this. I don't know if your professors really went over this much, but I hope this will help. So if you look at 5, you see this aldohexose here. These the preferred and actually I realized that before I even do anything with this, I really want to go over with you how to deal with what is chirality? What does it mean by a chiral carbon? So if you scroll over to the right where I am here on the Lucid Spark board, it says chirality and Fischer projections. Alternatively, you can also click back on the shared Blackboard Collaborate. But chirality and Fischer projections. So here's the deal. For something to be chiral, that means it's not superimposable with its mirror image. So think about your left hand. Your left hand is not superimposable with its mirror image. If you kind of think about it, like the mirror image of your left hand looks a lot like your right hand. It's basically like your right hand. But if you try to put your left hand over your right hand, you can see that they're not the same. They're not the same, and there's no way to make them the same. If you put there's no way to make them the same. You can never superimpose them so that they would be the same thing. And that has to do with the fact that your hand has 4 distinct different sides to it, so to speak. 4 distinct things coming out of it. So you have your thumb, you have your fingers, you have your wrist, and then you have an absence of anything on the other side. So whenever you have something that has 4 distinct sides to it, that's going to tend to make it chiral. And that's true also with carbon. So if carbon is bonded to 4 different groups, if carbon is bonded to 4 different things, then it's going to be chiral. It's going to be not superimposable with its mirror image. Okay? So If we're trying to analyze a substance for whether or not it has a chiral carbon, what we can do is we can look at the carbon and see. Well, the first thing I like to do is, check for the obvious. Does it have 2 or more hydrogens? If it has 2 or more hydrogens, it can't be chiral because for it to be chiral, you have to have 4 different things bonded to it. If you have 2 hydrogens, that means 2 of the things bonded to it are the same. So let's take a look at this carbon over here that I'm underlining in kind of a dark bluish purple. Is that going to be chiral or non-chiral?
Non.
Yeah, that's not chiral because it has three hydrogens, right? What about the next one?
Non.
It's chiral too.
No, that's going to be not chiral either because that has 2 hydrogens here. I'm a little bit further to the right, Frank. There you go. Yeah, so that second one's not going to be chiral either. What about the third one that I'm going to underline in yellow? Is that chiral or is it achiral? Well, the fact that it only has 1 hydrogen means at least that it could be chiral. Doesn't necessarily mean that it is chiral. But since it has only 1 hydrogen, it's possible. Let's look at the things that are bonded to it. It's bonded to a CH3. It's bonded to an OH. It's bonded to a hydrogen. And it's bonded to a 2-carbon group. Are those 4 different things?
Yeah.
Yes.
Yeah, they are. So that means that that carbon in the middle, that is chiral. That is chiral. So I'm going to go ahead and circle that with yellow to indicate that is a chiral carbon. It's bonded to 4 different groups. What about this last carbon over here? Is that chiral or no?
No.
No, it's not. So this is not chiral. So this one only has 1 chiral carbon. For number 2, let's see, we're going to have to look a little bit more closely.
There's no chiral at all in that one.
Yeah, okay, so this is, you have a hydrogen here. You have a hydrogen here. That carbon that was right here is not chiral because it has 2 hydrogens. What about this carbon? Is that chiral?
No.
What do you think? That one right there, is that
Yes.
chiral? So is it bonded to 4 different things?
Yes.
It's actually not.
I don't see
It
it.
has carbons attached to both sides.
Well, it
All
has
4
a
sides.
1 carbon, yeah, it has a 1 carbon group of CH3 on top, and it has a 1 carbon group of CH3 on bottom. And so those 2 are identical groups, 2 CH3s. So therefore, that is not chiral. If I look at the next one, this one has 2 hydrogens. Is that chiral?
No.
No, it's not. And the last one has 3 hydrogens, so we know that's not chiral either. So this one does not have any chiral centers. Therefore, the molecule as a whole is going to be what's considered achiral. So I'm going to call this achiral.
Oh, I see.
And achiral just means not chiral. Just like asymptomatic means not symptomatic. All right, so let's take a look at number 3. And I'll just go ahead and pop in the little hydrogens here just for, I won't draw the H's, but each of those little pink lines represents 1 hydrogen. So. All right. So what do you think? Is this molecule chiral?
Um, Isn't it the same as 1?
The third one has 4. No, the third one has 4 hydrogens, I think. 1, 2, 3, 4.
Oh,
The third one, yeah, that one. Does it have 4 hydrogens?
Well, none of them have 4 hydrogens. Okay, so so if we look at the first one, this has 3 hydrogens, so it can't be chiral. This has 2, can't be chiral. This has 2, it can't be chiral because 2 of the same group means it's not chiral. This one over here has 3, so that can't be chiral. The one on top is 3, it can't be chiral. The only one that could potentially be chiral is this one right here.
Yeah.
But is it chiral?
not really.
Look at the groups. Yeah, look at the groups that are bonded to it.
Oh,
You have this
okay.
one, this one, this one, and this one. Are any of those two the same, or are they all different?
They're all different.
No, actually not.
2 are the same.
Oh,
Yeah,
yeah.
this one and this one are the same thing. So because they're the same, this would actually be not chiral. I would have to call this achiral.
Wow.
Does that make sense?
Yeah.
Mm-hmm.
Let's try to do number 4. Is that chiral or achiral? What do you think?
Achiral?
The chiral.
Achiral. Yeah. Very good. Because if we're looking at this, you have 3 hydrogens on this one, so that's not chiral. 3 hydrogens here, so that's not chiral. Now, if this one, that one right there, doesn't have any hydrogens, it could be chiral except for the fact that this group, this CH3 and this CH3 are the same. So it's not chiral. This one has 2 hydrogens, so it's not chiral. Anything with a double bond cannot ever be chiral. So this one in blue here, anything that has a double bond can never be chiral. Okay, so that's not chiral. All right, so let's look at number 5. What do you think? Is that chiral or achiral?
So, chiral? No, achiral.
Achiral.
Sorry.
Achiral.
Well, all I mean is when I said if it has a double bond, then
Yeah.
that carbon can't be chiral.
Oh,
So,
okay.
not that the molecule can't be chiral. A different carbon can be, but that blue one I've marked right there can't be chiral because it has a double bond. But the rest, there could be a chiral center somewhere else. Are there any chiral carbons in this molecule?
No.
Actually, there is.
1, 2,
Let's
3.
take a look at it.
Oh,
So,
okay.
That's 3.
yeah, 3 hydrogens here, 3
That one is
hydrogens
3.
here. So that one can't be chiral. This one has 1 hydrogen here,
That's 2.
but it can't be chiral either because this is the same as this. But if I look at this next one here, there's a hydrogen there. If I circle the 4 groups around it, I have a CH3 here.
Oh.
I have a big group over on this side. I have a hydrogen. And I have this over here. Are any of those 4 groups the same?
No.
No, they're all different. So that means that that is in fact, this carbon here is in fact a chiral carbon. It is a chiral center. And therefore I would call this molecule chiral. Whereas this one was achiral. All right, I'm going to give you guys a shot. I want you to do Let's see. Leanne, I'm going to have you take 6. Linda, I'm going to have you take 7. And Frank, I'm going to have you take 8. Leanne, move your cursor over to the right. You can turn it into a hand and drag it over, drag the screen over. Turn your arrow to a hand, drag it over to the right. There you go. So
Mine is a Chiral.
You said that yours is achiral?
Yep.
Good job. Yeah. Linda, yours is achiral. Very good. Frank says his is achiral as well. Very good. No chiral centers there. Leanne's still thinking about it.
6 is a Chiral.
Chiral. Yeah, yours is chiral. Very good. Now, where is the chiral carbon? Can you put a dot on the chiral carbon?
But in this one, you have 3 here, you have 3 here now. They're not the same thing. 3 here, 3 here. This is different. This is different from this one.
Now, that is actually not the chiral carbon.
It's a chiral.
So here we got 3 hydrogens there. There's 1 hydrogen here. There's 2 hydrogens here. Yeah. So that one in the middle had 2 hydrogens. So that's not chiral. And the one over, once again, you have 2 CH3s attached to
that middle.
Attached to this one.
That's 3.
So that one's not chiral either. Yeah, the one that is chiral is going to be.
That one looks like a chiral. It's like chiral, but
that's your chiral carbon here. Yeah, that's your chiral carbon on 6 because it has 4 different groups attached to it.
No, the way I'm looking at it, okay, if where you have that middle there between that H, okay, this if you add all those together, that's 1. This is 3. This other one is 3. Oh,
what are you talking about? What question are you? What question are you talking about, Linda?
I thought you were using the dots that links the OH and the other blue one. This green, the green in the middle. I thought that's the one you were using.
Oh no, I was just I'm pointing that one that is circled darkly. That is your chiral carbon because it's bonded to 4 different groups.
Okay.
This one in the middle was not chiral because it had 2 hydrogens attached to it.
Yeah.
All right, cool. All right, you feel like you got a pretty good understanding of this chiral carbon stuff? You probably won't be expected to do a ton with it, to be honest with you. You probably will not be expected to do a ton with it. So I'm not going to spend a tremendous amount of time going over it. But if you can shift your focus back to where the first page was, shift your focus down towards the bottom. Frank, you're a little too high. Just drag your screen down. Use the little hand. There you go. So that's where I am. I want to look over here, and Leanne, you can just come down, drag your screen down, the little hand. There you go. I want you to look at some of these Fischer projections because the Fischer projections are how we can determine if some things are like mirror images or not, or if they're the same compound. If you look at number 2, these Fischer projections these Fischer projections, the way that they're drawn, does not necessarily clearly show the stereochemistry. Essentially, what's happening is that these 2 out to the side are wedged. They're coming towards you. And the 2 going top and bottom are dashed. They're going away from you. okay? They're going away from you. The top and bottom are going away, and the two sides are coming towards us. All right. So if I look at this, would the compounds, the two compounds here for number 2, are they mirror images of one another?
Yes.
And one of the ways you can tell is to draw kind of like a line of symmetry right across the middle. Is one a reflection of the other? Are they mirror images of one another?
Yes.
So
Yes, they are.
they use. Okay.
What were you going to say?
I was going to say, if you, so are you saying that if you put one on top of the other, would it be the same? But if it's
No,
not,
if you
you're
put
saying
one on
there's a
top of the
mirror,
other, yeah, if you
yeah, that
put one on top of the other, they would not be the same.
that's right. Okay.
No.
And there would be no way to make them the same.
Okay.
Yeah. All right, cool. So, so that means that these are enantiomers. Enantiomers are non-superimposable mirror images. They'd be like your left hand and your right hand. Those are enantiomers. All right, so now let's take a look at number
So
4.
your hands.
Oh,
So
yeah, go
your
ahead.
hands are. Oh, sorry.
No, go ahead.
Oh, so your hands are achiral and enantiomers.
No, they are chiral. They are
Chiral.
chiral. They're chiral enantiomers of one another. They're
Okay.
non-superimposable mirror images. Exactly.
Okay. Cool.
And that's because of the three-dimensional nature of your hand, and that the front of your hand is different than the back of your hand, and you have the 4 different sides there. With these chiral compounds, if a carbon is bonded to 4 different groups, it is chiral, which means that its mirror image will not be superimposable with the image. I wish I could show you the models because it's easier to see with the molecular models than it is with these 2D representations. But uh, you would not be expected to um, uh, do a tremendous amount with this. It'll be fairly simple. The key thing with the enantiomers is that, and with these Fischer projections, is that carbons that are chiral, or at least have the potential to be chiral, are always shown in the crosshairs. Like, so if you have cross like this, this, and this, the carbons that either could be chiral or are chiral are going to be the ones, are going to be the cross ones. Like this, this one, or this one. They're not going to be the group down here, and they're not going to be the group up here, for Fischer projections, that is.
Okay.
Okay. Furthermore, enantiomers, the only thing that should switch, the only thing that needs to switch is the, or flip sides, I guess you could say, is the chiral carbon groups. So in other words, if this is H and this is Cl, and this is, let's say, Cl, and this is H, and this is OH, H, and let's say this is H and H. Well, this is H and H, the two H's, so that's not chiral, that carbon. But the rest of these ones are. And so, for example, if I want the mirror image, that means the H for this one has to be on the left side, whereas in the other one it's on the right side. The OH then has to be on the right side, whereas in the other one it was on the left side. The H's here doesn't matter because they are both H's, it's not chiral. The Cl, once again, I have to flip the sides, so the H is going to go there and the Cl is going to go on the right, whereas before it was on the left. And then the last one, Cl goes on the left because before it was on the right, and then the hydrogen goes on the right because before it was on the left. And regardless of whatever is here and here, as long as the top groups and the bottom groups are the same, these two would be enantiomers. Okay, so let me have you.
So hold on. If they mirror each other, right? It
They
means that
mirror
they are
each other,
enantiomers.
exactly. They're non-superimposable mirror images, and so I'll go ahead and draw the mirror. So you can see that they're mirror images of one another. All right, what about number 4? Are they enantiomers or are they not enantiomers?
No, they're not.
Not.
They're not. They're actually the same. They're actually the same exact compound, right?
Mm-hmm.
And the reason is because one thing you have to keep in mind is that you can always rotate around a single bond. Uh, with the top and the bottom, you can rotate around a single bond without changing what it is. So if I rotate this around here, you see that you get this. Yeah, yes, this double bond O is on the left side here and on the right side here, but that doesn't make a difference because that's trigonal planar. Whereas the sides, remember with these Fischer projections, the sides here are wedged and dashed. Okay, are wedged and then the top is dashed. All right. And so yeah, basically, the carbon with the double bond O, that's flattened because of the double bond oxygen. And you can rotate around that top bond and you can rotate around that bottom bond without it being a problem. Like it's not going to alter the stereochemistry, but with the chiral one, uh, I mean, those are pretty stuck there. Even if I rotate, uh, if I rotate any of those bonds, they're still in the same relative position around that middle carbon. All right. For the number 3, this is the only one that's a little bit tricky. One of the things that you can do here for a chiral carbon um, is a tri-rotation. Okay. If you want to retain stereochemistry, you can actually get a different structure. You can move these such that they are rotated. We can rotate 3 of them and get something that's the same as what you had before. So like for example, if I wanted to compare this one with this one, I can only do it if the top group and the bottom group are the same. So what I'm going to do is I'm going to take that first group here and I'm going to rotate the hydrogen to the bromine to the chlorine, and the chlorine to the hydrogen. Now you can only rotate 3. You can either hold the top constant and rotate the bottom 3 clockwise or counterclockwise, or you can hold the bottom constant and rotate the top 3 either clockwise or counterclockwise. That's the only way you can rotate these. And this will become important for what we're about to do with the Hayworth projections rather. So if I rotate this around in the manner that I've shown, the fluorine stays on the top. What atom is going to be on the right-hand side now?
Chlorine.
Yeah, the chlorine, right? And what's going to be on the bottom?
Hydrogen.
Very good. And what's going to be on the left-hand side?
Bromine.
Bromine. So if I'm looking at this now, and I drag this one down here, or just redraw it, hydrogen on bottom, chlorine on top, chlorine on the right, bromine on the left. Are these the same compound or are these enantiomers? They're the same. They're exactly the same. Yep. Everything is exactly the same. They're not mirror images, They're literally exactly the same. The bromine is on the left, chlorine is on the right, hydrogen's on the bottom, fluorine's on the top. So these are the same.
They're identical structures.
Identical. Yep. Just like these are the same. Very good. Well, let's scroll up and let's go to the, let me drag my screen over to the left. Going back to our problem number 6, problem number 5, the aldohexose. There we are. You guys are in the right spot. All right. So if I want to turn this into a Hayworth projection, what I have to keep in mind is these Hayworth projections tend to form either what are known as furanose rings or purinose or furanose. And the furanose rings, and that's just, those are just fancy names. And I'll go ahead and purinose rings are basically six-membered rings of monosaccharides. And then furanose rings are basically, a furanose is just a five-membered ring formed from a monosaccharide. And what you might notice is that actually these furanose and some molecules can actually do both a furanose and a furanose ring, but furanose rings usually are preferred if it's possible because they will tend to give you the most stable ring structure. Okay, so what I'm going to do is first to come up with the Hayworth projection for this, I'm going to take this. Well, actually, let me go ahead and I'll draw it here. I'm going to take structure number 5, and I'm going to rotate it. I'm going to turn it down on its side. Okay? So see if you can tell where I'm getting this structure from. Okay? I have oxygen, hydrogen, and I have the first one, hydrogen on top, OH on bottom. Second one, OH on top, hydrogen on bottom. Third one, OH on top, hydrogen on bottom. Fourth one, hydrogen on top, OH on bottom. And then there's also this CH2OH. Can you see where that came from? How I just tilted that structure over?
Yeah.
I rotated it clockwise. Okay, cool. So now here's the thing. Usually it is the hydroxide from the last chiral carbon that attacks. You know, the one that causes it to be either D or L? That hydroxide from the last chiral carbon is the one that attacks the carbonyl, it adds to it. So my next step for this, drawing the Hayworth projection, is to do what I taught you how to do, to rotate the 3 groups with the Fischer projection. So I'm going to rotate these 3 groups. I'm going to rotate, I want to get the OH out in the back. So I'll rotate the OH out and back. I'll rotate the CH2OH up here, and I'll rotate the hydrogen down here. Now I'm going to redraw my molecule, and this is what it's going to look like. And so this H is still going to be up, OH is still going to be down. This OH is still going to be up, this H is still going to be down. This OH is still going to be up, this OH is still going to be down. But now that I've rotated the other three on this last one, I have a
CHOH.
CH2 OH here. I have an OH back here, and I have an H down here. So now here's the thing. I am now going to go ahead and attack I'm going to take it's actually the electrons on this oxygen here that are going to go around here and attack. They're going to attack that carbon right there. And that's going to cause the double bond to become a single bond and send electrons up here. Okay. Essentially what happens is, I wanted to be totally clear, I'm going to draw this hydrogen out here in red. Okay. And I'm going to draw, what's a really standout color?
Red. This is red.
Sure, I'll actually use this bright blue because I think this is important. Okay, this oxygen here, I'm going to make this light blue or purple or whatever the heck that is. I'm colorblind, I don't know. All right. So now I'm going to draw my ring structure. It's going to look like this. So this is my Hayworth projection. And here's my oxygen in the middle of the ring. That oxygen in the middle of the ring is that bluish purple or whatever the heck that is that attacked from the previous one. Notice if you actually look that it comes around and attacks from on top, you notice that that's why it's there. Now let me go ahead and number these. Let me go ahead and number these carbons. This is carbon number 1, 2, 3, 4, 5, and 6. Okay? So 1, 2, 3, 4, 5, and 6. Well, and that if that's the case, I have to recognize that this is 1. Because this is the one that carbon number 1 was the one that got attacked by the oxygen. So this is my 1. This is my
Why is
2.
the 6? Why is the 6 at that other end? They're not at the tail end.
Well, because I'm numbering the carbon chain. I'm not numbering any others. I'm not numbering oxygens, right? So this is 1, 2, 3, 4, 5. Okay. So if I'm looking at carbon number 2, then this carbon, I know that I have the hydrogen is in the up position and the OH is in the down position. For carbon number 3, the OH is in the up position, just like before, and the H is in the down position, just like before. For carbon number 4, likewise, the OH is in the up position, and I can put the H on either side really, and the H is on the bottom position. Now for carbon number 5, I have an H in the bottom position, but what do I have in the top position for carbon number 5? Yeah, I have a CH2OH. Now, carbon number 1 is interesting because here's the thing. Because that is a double bond, that end right there, it really could have been drawn either like the double bond could have been rotated down here and the hydrogen could have been up, or the double bond could have been up and the hydrogen could have been down. Depending upon where it was when it was hit, you can have either the oxygen be up or it can be down. If the oxygen ends up being in the up position, and by the way, it ends up stealing that hydrogen. Do you remember that hydrogen that I marked in orange in the other compound? Here's where that hydrogen went. It used to be attached to that purpley lighter blue, but now it's attached to the carbonyl oxygen. Now, if that OH is in the up position, this is what we call the beta. This is what we call the beta anomer. If, however, I drew the exact same thing in every way, and except that, of course, this would be my blue one. Yep. But, and everything was the same except that the OH and the number 1 carbon ended up being down. This would be the alpha anomer. And of course, the rest of this is quite the same as well. I still have the OH on the bottom for carbon number 2, and an H on top. Carbon number 3, OH is up, H is down. Carbon number 4, OH is up, H is down. Carbon number 5, CH3OH is up, CH2OH rather, and the H is down. And just for consistency, that hydrogen that is red is now attached to that oxygen that was the carbonyl oxygen. So that's how you draw these Hayworth projections. And I know that this is a little bit tricky, but if you follow these steps, you'll be able to do it. Turn it over to the side. Rotate the last 3 groups so that the oxygen is going out in the back. Have that oxygen come back around and attack it. And you'll get the alpha and beta anomers. Now, your professor may or may not expect you to do these Hayworth projections, but even if they don't expect you to actually write the Hayworth projections, they will expect you to distinguish between alpha and beta anomers.
What's the difference? Is it because you rotated the OH and the H that is why it became alpha and beta?
Yeah. If and the key difference is this: if the OH is up, it's beta. If the OH is down, it's alpha.
If the OH is up,
if the OH is up, it's beta, and if it's down, it's alpha. So,
it's alpha, right?
And a beta sugar has the OH going up on that anomeric carbon. Now, what does it mean by the anomeric carbon? The anomeric carbon is this special carbon. I want to circle it in a special color. We'll do this color. This carbon right here that I'm circling here, and the carbon here that I'm circling here. That carbon is called the anomeric carbon. It's the only carbon that is, so the anomeric carbon is what determines whether or not it is the alpha anomer or the beta anomer. That's why it's called the anomeric carbon. And you can always tell the anomeric carbon because it is the only carbon bonded to 2 oxygens. It's the only carbon bonded to 2 oxygens. If you look at each one of those other carbons, each one of the other carbons is bonded to only 1 oxygen. Okay? Carbon number 2, 1 oxygen. Carbon number 3, 1 oxygen. 4, 1 oxygen. 5, 1 oxygen. 6, 1 oxygen. Only carbon number 1 is bonded to 2 oxygens. It's bonded to the oxygen in the ring and the oxygen here. That carbon is the only one that's bonded to 2 oxygens. That is the anomeric carbon. And that also has to do with determining whether or not something is a reducing sugar, because a reducing sugar is any sugar that has a hemiacetal. And now hemiacetal, now go ahead and write out what a hemiacetal is.
And in what?
Hemiacetal. A hemiacetal is when a carbon is bonded to an oxygen and an OH. So it's bonded to just an oxygen by itself and an OH. So for example, what we have here is a hemiacetal because you can see that that carbon, the anomeric carbon, is bonded to an OH, but it also is connected to an oxygen which doesn't have an H. That's called a hemiacetal. If something has a hemiacetal, it is a reducing sugar. All monosaccharides are basically reducing sugars. Okay?
Yeah.
All right. So, to that extent, let's take a look. Let's take a look at some of these disaccharides and the glycosidic bonds and see if they're reducing sugars or not. Scroll right down, and you can see it gives these disaccharides. So let's look at the first one, the beta lactose. Okay. I'm not sure where Leanne is, but Frank, you're in the right. Yeah. Okay, Leanne, a little bit over to the left. Okay, there you go. Yep. So if I'm looking at beta lactose, okay, so that's this one, beta lactose. First of all, the compound, it's given to me as lactose, and the bond that connects 2 monosaccharides is known as the glycosidic bond. So the bond connecting 2 monosaccharides is the glycosidic bond. So that would be this bond right here. This is the glycosidic bond right here. Okay? That's the bond connecting the 2 monosaccharides. Or one could even consider both of these as part of the glycosidic bond. So that is the bond connecting 2 monosaccharides. Okay? Now these sugars can be, the disaccharides can be classified as either alpha or beta sugars, depending upon how the, you look for the anomeric carbons first, okay? So the anomeric carbons are the carbons that are attached to 2 oxygens. In the first ring, the anomeric carbon is here. I've marked it in yellow. In the second ring, the anomeric carbon is here. I've marked it in yellow. At least I think it's yellow. Okay? Since the glycosidic bond only involves 1 anomeric carbon, I only make 1 designation. In this case, is the O is the oxygen attached to the is the oxygen attached to the first anomeric carbon? Is it going up or down?
On the lactose?
Yep. On the left-hand ring, is the anomeric carbon
Okay.
up or down? Is the
Up.
oxygen up or down? Up,
Up.
which means it's what? Alpha or beta?
Beta.
Beta.
Beta. And so this is going to be a beta. This is going to be a beta linkage. Now, the other one has beta as well, but it doesn't matter because even though this is beta as well, this is not the one that determines, this is not the glycosidic bond. It's not part of the glycosidic bond. So I don't care about the fact that that's beta up here. But because this has a beta linkage connecting these two, I would call this beta lactose. If these same two sugars were connected, but the oxygen was pointing down, in other words, this one here was actually underneath it because the oxygen here was down, then that would be an alpha lactose. In this case, we have a beta lactose. And then we also, so the type of glycosidic bond, if you wanted to classify it, would be a beta 1,4 glycosidic bond. You might be like, well, why 1,4? Well, in the first ring, this is carbon number 1, and then I have carbon number 2, and then 3, 4, and 5, and then 6 up here. In the second ring, I have 1, 2, 3, 4. So you see, it's carbon number 1 of the first ring is connected to carbon number 4 of the second ring. So that's why this is called beta 1,4 glycosidic bond. Does that make sense?
Yes.
Yeah.
Okay, cool. Now what would number 1 be? Would this be, so first of all, can you go ahead and draw a little circle on the anomeric carbons? Find the anomeric carbons for me on number 1. Remember, the anomeric carbon has to be connected to 2 carbons, or 2 oxygens. The anomeric carbon has to be connected to 2 oxygens. And you can draw a little circle on it if you want.
So I've hit the 300 object limit and it's asking me to do a free trial.
No, don't worry about it. All right, very good.
It's
Fudge,
doing the same.
okay.
Yeah. So
it's doing
yeah,
the same
your anomeric carbons are these two. Your anomeric carbons are these two. So that's the anomeric carbon. Okay. So in this case, we only have one anomeric carbon that's involved in the glycosidic bond, right?
Yeah.
Can you put your little cursors, your little arrows where the glycosidic bond is? Point to the glycosidic bond.
Is it in here?
Yeah, there you go.
That's an alpha.
Those are the glycosidic
Alpha
bonds. So
lactose?
that's the glycosidic bond, basically right here, here. Yeah, that's your glycosidic bond, the linkage connecting them together. Now, is that first anomeric carbon that it's connected to, is that an alpha linkage or is that a beta linkage?
I think it's alpha because it's down.
It's alpha. Yeah, exactly. It's down. So this is an alpha glycosidic bond, and therefore we would have to call this structure alpha maltose. It says it's maltose. This is alpha maltose. Does that make sense?
Yeah.
All right. So now, what type of glycosidic bond do we have? Well, what
Beta,
number
I guess.
carbon is? Oh yeah. So what were you going to say? Go ahead.
No, I thought you were talking about number 2.
Oh no, I'm talking about number 1. So what is the glycosidic bond?
Beta. No, I mean alpha 1,4 maltose. No. Yeah.
Yeah, and well, yeah, no, it's you could just say call it an alpha 1,4 glycosidic bond. That's fine.
Okay.
But yeah, it is an alpha maltose and it's alpha 1,4 glycosidic bond. Excellent, excellent. Now you see, does maltose have? Well, okay, let me ask you this: does maltose have a hemiacetal?
I don't know.
Okay, so look at the two anomeric carbons, because only an anomeric carbon could potentially be a hemiacetal. In other words, is it attached to an OH and an O?
With an oxygen and
Yeah,
and
so the left
I
one's
think
not,
yes.
right? The left one's just attached to one oxygen on one side, one oxygen on the other, right?
Yeah.
But the right one is. It's attached to an O on one side and an OH on the other. So that's a hemiacetal. So that means that the maltose is a reducing sugar. It can be reduced, or it can be oxidized. It is a reducing sugar. Okay. Likewise, if you look at lactose, there is a hemiacetal here. So that would likewise be a reducing sugar as well. Let's take a look at sucrose. Okay, so first of all, let's identify the anomeric carbons. Can you put your cursor on one of the anomeric carbons for number 3, sucrose?
Anomeric. Here. Well.
Yeah, right there, exactly. So here's an anomeric carbon, right? Where's the other one? Yeah, there you go. Both of those carbons are connected to 2 oxygens, right?
Yeah.
Yeah.
Now, in this case, this is interesting because both of the anomeric carbons are connected to each other. So the anomeric carbons in this case are connected to each other. Because of that, this would not simply be an alpha sugar or a beta sugar. I would say, okay, so the ring on top is what? Is it alpha or beta?
Beta.
The ring
No,
on
wait, it's
top?
alpha.
Yeah.
Yeah, it's
So the
alpha
ring on
there.
top is alpha because the oxygen's going down. The ring on bottom is what?
Beta.
Yeah, so this is alpha beta. So this is alpha beta.
Wow.
Now, if I wanted to describe the glycosidic bond, I would actually have to say that I would call this alpha, comma, beta, dash, and what is this number carbon here? In the first one, this is carbon number 1, right?
Yeah.
What about the second one?
So number 1 also.
Actually, carbon number 1 is right here.
Oh.
And it's weird because normally you would think to start numbering in the ring. It's a little bit different because you have to look at what the chain was beforehand. So this is a fructose molecule. So and for these carbohydrate rings, the numbering starts out just a little bit differently. You would call this number 1 and this would be number 2. So this is an alpha beta 1,2 glycosidic bond. It's pretty messed up, right?
Yeah.
Fortunately, I don't think you'll have to deal with anything quite that complex. And admittedly, this is what if I wanted to be a real stickler, what I would basically say is what really causes it to be alpha or beta is not simply that it goes up or down. What really causes it to be alpha or beta is the fact that the oxygen attached to the anomeric carbon and the group attached to the last carbon in the ring before, that's also connected to the oxygen, the attacking oxygen, are on opposite sides. So remember that this position here, this determines on whether or not it's D or L. You remember that? Like just like this one here, this determines whether it's D or L. This one here determines whether it's D or L. If you opened up the chain, that carbon that's connected to this oxygen in the middle of the ring, the carbon that's connected to the attacking oxygen in the middle of the ring, that's the carbon that determines whether it's D or L. If that carbon has its larger group in the opposite direction as the anomeric carbon, it's alpha. If they're on the same side, it's beta. Not to overly confuse you, but if they're on opposite sides, it's alpha. If they're on the same side, it's beta. So like, for example, the sucrose here has this group on the same side as it's the oxygen coming off the anomeric carbon. This is why this is an alpha. Or rather, this is a beta. It's a beta sucrose, or beta fructose that's attached to the glucose on top. On the top, the CH2OH and the oxygen are on opposite sides. And on the bottom, the CH2OH and the oxygen are on the same side. So if it's the same side, it's beta. Opposite side, it's alpha.
Okay.
I know this is a lot to take in.
Yeah, it is.
There's the good news is that there's a lot of once if you look at these and you do look at the practice problems and you look at the answer keys to the practice problems and you try some of these, you're going to start to notice some of these consistent patterns and it's going to make sense. And it's going to make sense why. Okay, this is alpha. Okay, I see. That's why that's alpha. This is beta. Oh, that's why it's beta. Okay, and you'll be able to kind of get the hang of it. Usually, the professors don't test too difficult on the carbohydrate stuff because, to be entirely honest with you, the carbohydrate stuff is kind of complicated when you really dig into it, and they're really not taking the time to really dig into it. They're not taking the time to give you a full understanding. So it can't be expected for you to have a full understanding.
Okay.
But one quick little thing here. I'm going to erase some of this extra stuff here. Let's look at the two anomeric, or let's look at the anomeric carbons in sucrose and tell me, does this have a hemiacetal?
Hemiacetal is
No.
Linda, did you say no?
Yes. I can only
You're
see
correct.
O. I don't see where the
Yeah, exactly. So if you look at, I mean, the top anomeric carbon is connected to this one and this one. They're both oxygens. Neither one is an OH. The bottom anomeric carbon is connected to this one and this one. So in both cases, oxygens that they're connected to are oxygens. They're not OHs. Neither one is an OH. So these are not, there's no hemiacetal here. So this is why sucrose is a non-reducing sugar. This is why it gives a negative result
because it
for
is
testing for
no,
reducing sugars. Sucrose is
because
not a
it is not
reducing sugar
hemiacetal.
because it has no acetal. Or it has no hemiacetal. Exactly. Awesome.
Let me take the photograph. Hold
Well,
on, let me take the photograph.
Yeah, absolutely. Please do.
Okay, done.
So I wish we could have taken some time to go over some. Actually, you know what? We did start a little bit late. I just want to go over some real easy thing that you're almost certainly going to be tested on. I just want to make sure that you have a bit of an understanding of. If you go straight up and a little bit to the right, I'm going to drag my screen over that page with the pictures with the little like curly cues and things. Yeah, there you go. Yeah. So this is classifying it as a reducing sugar or a non-reducing sugar. Now you know how to do that. And we can also classify it as a monosaccharide or disaccharide or a trisaccharide. I mean polysaccharide rather.
Poly, yeah.
Mm-hmm. So monosaccharide just means a single sugar, essentially a single ring. It's not going to be connected to any other rings. A monosaccharide can go into ring form or it can stay out of ring form. Generally speaking, they're in ring form and they're drawn like this. So, question number one, is that monosaccharide or disaccharide?
Mono.
Monosaccharide, very good. And so monosaccharide, is it a reducing sugar?
No, you can't reduce monos or disaccharides.
It has OH and H. It's a hemiacetal.
Hemiacetal. This is a reducing sugar.
It's a reducing sugar.
Yeah, all monosaccharides are reducing sugars.
Oh.
All monosaccharides have hemiacetals. Okay. What about number two? Monosaccharide or disaccharide or polysaccharide?
Poly.
It's
Yeah, it's poly. There's lots and lots of sugar rings here. Polysaccharide, absolutely. Okay. And now polysaccharides are never reducing, so we don't even have to worry about that. Let's look at number three. Monosaccharide, disaccharide, or polysaccharide?
Disaccharide.
di.
Yep, disaccharide. Very good. And is it a reducing sugar or a non-reducing sugar?
Non-reducing sugar.
What'd you say?
None.
No, it is.
Oh, yeah. Okay, it's a reducing sugar. I didn't look at that. I was looking at the other one. Okay.
Yeah, you got to look at
that one
both.
doesn't have a OH.
Yeah, you
Okay,
always
have
got
to
to
look
look at
both,
both.
right? Okay.
Yeah, both anomeric carbons, not just one. Because even if there's only just one hemiacetal, it's going to be reducing sugar. So this is a reducing sugar. I'm going to put reducing. Reducing. And I'll put reducing here. What about sucrose? Monosaccharide or disaccharide or polysaccharide?
Mono.
Die.
I don't remember it by heart.
Yeah,
That's
and
sucrose again.
this,
Can you go back to
unfortunately,
let me look at it?
they do have a few disaccharides that they expect you to memorize by
Disaccharides.
heart. And the ones they expect you to know are sucrose, maltose,
And it is a non-reducing sugar.
and sucrose, maltose, and lactose. They expect you to know those ones.
Does that
Sucrose,
include
maltose.
And these are all
Sucrose,
disaccharides.
maltose, and with sucrose, maltose, and what?
And lactose.
Lactose. Okay.
I have them off to the right. Now you have to know that sucrose is composed of glucose
And the fructose.
and fructose. Very good.
Don't remind him.
It's composed of what? What's composed?
And you also need to know that maltose is composed of what?
Glucose and glucose.
Yep, two glucoses.
Maltose is composed of what? Is composed of what?
Two glucose molecules. A glucose and another glucose.
I don't know it.
That was That was sloppy. I'm gonna type it.
Glucose and glucose.
Okay. 2 glucose. right? That's maltose. And then lactose is composed of what?
Galactose and glucose.
Lactose is composed.
Yeah, glucose and galactose. Glucose
Galactose?
and galactose. Galactose. So there we go. Glucose and galactose, that's what lactose is formed from. Okay. So sucrose is glucose and sucrose, maltose is glucose and glucose, lactose is glucose and galactose. All right. So glucose, sucrose is a disaccharide, and it is going to be non-reducing, right? Non-reducing.
Yeah, non-reducing sugar.
Cellulose is also one they're going to expect you to have memorized. They won't tell you what it is. Is that a monosaccharide, disaccharide, or poly?
That's a poly, right?
I don't know.
Poly, yep. That's what wood and trees and plant matter and all that kind of stuff is built out of cellulose, polysaccharide. Polysaccharide. Polysaccharide.
All I remember from that one is that you can't digest it.
What about glucose?
Sugar, mono can't be reduced.
Yeah. Well, no, it's monosaccharide, and is it a reducing sugar?
Non-reducing.
No, it's reducing.
No, it's reducing sugar. It's
Always
reducing.
Yeah.
Okay, I got them backward.
Yeah.
Great.
What about 7? What does that look like?
Cellulose.
Mono, di, or poly?
Oh, it's a poly. Sorry.
Yeah, look at all those tiny little rings. The tiny little rings, those are actually big sugar rings. So polysaccharide, absolutely.
Monosaccharides, are they reducing or non-reducing? What are they?
Yeah, that's amylose. And then, so I think you guys probably get the idea at this point.
Yeah.
Are they reducing or non-reducing? Are they reducing or non-reducing the polysaccharide ones?
They're always non-reducing because they never have a free hemiacetal. Because remember, a hemiacetal has to be one of the anomeric carbons, right? The problem with polysaccharides is that the anomeric carbon is always connected to another anomeric is always connected to another ring. So you don't see any. There's no connection that's not that's open for being reduced for being oxidized to allow it to be a reducing sugar. Now look at number 10. You know that's a disaccharide. Is that a reducing sugar or a
Could you take it down?
non-reducing?
I can see you. Can you take it down a little? I can see this from the screen. I can see number 10. 10 is disaccharides.
It is a disaccharide. Is it reducing or non-reducing?
It is reducing.
It is reducing. No, it is not reducing.
You have the OH and the H there.
Nah, but you don't have an OH and an H bonded to the same oxygen.
Are you talking about number 9 or number 10?
But you don't have an OH and an H. You don't have an OH and an oxygen bonded to the same carbon. Remember, you got to look at your anomeric carbons. So your anomeric carbons for number 10, this one's connected to 2 oxygens, and this one's connected to 2 oxygens.
Oh shoot, I'm looking at something else. Okay.
Yeah, none of the others are connected to 2 oxygens. So if I look at those 2 anomeric carbons, neither one has an OH attached to them. So they can't be anomeric. I mean, they can't be reducing sugars because there's no hemiacetal.
Yeah. Was it disaccharide, right?
Yeah, it's a disaccharide. So it's non-reducing and it's a disaccharide. If you want some more information on this, I do have a number of really good videos up on our website that can also expound on this a little bit more. But I do hope that this session was helpful, at least somewhat, for your understanding of carbohydrates.
Yeah.
Yeah, definitely.
Well, thank you so much for coming. We'll have our last learning workshop next week on Tuesday over proteins and amino acids and enzymes. And I look forward to seeing you then. Thank you so much and have a great week.